Hello students, today we are going to learn about how to find out the shape functions or the stiffness matrices for a quadrilateral element of irregular shape. So earlier we had worked with the rectangular element, so which had height and length which were not the same. However, the two sides were parallel. So meaning that earlier we had element like this where we had this type of element where this side and this side were parallel. Similarly, this side and this side were parallel, and it had angle, all angles 90 degrees. Now instead of this one, if we want to have a finite element analysis for irregular size and shape, which could be something like this one, then we want to learn how to deal with this kind of element. So let's say we have this coordinate system xy, and we have this element which goes like this. So we have element this node number 1, 2, 3 here, 4, number 4 here, and the corresponding coordinates are here x1, y1, this x2, y2, x3, y3, and x4, y4. Then as there are 4 nodes, there will be 4 shape functions n1, n2, n3, and n4. The usual way will be to define ni xy as alpha I plus beta ix plus gamma iy plus delta I xy, as we did for rectangular element, and we do the analysis, similar analysis, meaning that we will make ni xj yj is equal to delta ij, where delta ij is Kronecker delta, meaning that delta ij equal to 1 if I equal to j, or equal to 0 otherwise. That is when I not equal to j. So this analysis we have been doing, and this is also a lengthy process. It's not difficult, but it requires lot of time in order to evaluate these constants, the coefficients, delta i's, beta i's, gamma I, delta i's. So the shortcuts, for example, for rectangular element we had a different shortcut, and we, instead of finding out, solving the linear problems, solving 16 equations to find out the 16 coefficients, instead of doing that, we directly applied some insight and evaluated ni's directly. Similar fashion also we can do it here, and for that we'll have to transform this shape into a square shape. And this method is, or this kind of element where you change from one coordinate system to other coordinate system, which is easier to solve, is also known as isoparametric element. Parametric element. Okay. What is the meaning of that? So the original element will be converted into a known form, something like this. This is a square basically. And let's say the coordinate systems are like this. So this is coordinate system is, this is xi and this is eta. Okay, and we are, the whole domain omega is now transformed to a square domain with this corner point. This one is node 1, this is node 2, this is node 3, and this is node 4, and such that the coordinates are -1, -1. Here this is 1, -1. This is 1, 1, and this one is -1, 1. Okay. Now the question is how to develop the shape functions for this one, or finally how can we calculate the stiffness matrix. So first we have to see what is the transformation law, meaning that from one coordinate system to the other coordinate system, how you transfer. So basically in order to transfer from one coordinate system to other, what we have to actually write one equation which relates the two coordinate system. So here we can write x as x equal to let's say we say n1, n2, n3 and n4, and here we write as x1, x2, x3, x4. So here it goes like this. Yeah, so that means we write x as a function of n1, n2, n3, n4 multiplied by a vector x1, x2, x3, x4, where n1, n2, n3, n4 are function of xi and eta now. So these are a function of xi and eta. Okay. And similarly we have y, we can write it as n1 function of xi eta, n2 is a function of xi eta, n3 function of xi eta, n4 which is a function of xi and eta, and then a vector here which will have y1, y2 and y3, y4. Okay. Or simply we write x equal to summation of ni is xi eta multiplied by xi from I equal to 1 to 4, and similarly y equal to summation of I equal to 1 to 4 ni xi eta multiplied by yi, where xi, yi is the coordinate of the ith node, where ni xi eta we have to find out. What is the meaning of ni xi eta is here in the transformed coordinate system. So we have xi here and this is eta here. This is a transformed element now. As I said earlier, this is node 1, node 2, node 3, node 4 with the coordinate system -1, -1. This is 1, -1. This is 1, 1, and this one is -1, 1. So for this one for this coordinate system, if we have to define the shape function for these 4 nodes, then we can easily do it, meaning that we can find out this equal to ni xi n equal to we can find out what is the, so this is xi 1 this is xi 1 eta 1, xi 2 eta 2, xi 3 eta 3, xi 4 eta 4. Then eta I xi eta will be equal to 1 over 4 1 minus xi I multiplied by 1 minus eta I. Rather it will be xi plus xi I and eta plus eta I, then divided by 4. This is because ni should be 1 at xi I eta I. So if you write xi I here and eta I here, then this becomes 2 xi I 2 eta I. So 1, it has to be 1, so this will be 4, has to be divided by 4 xi I and eta I. So we write it again, repeat here. So eta I xi eta will be equal to 1 over 4 xi I eta I multiplied by xi plus xi I eta plus eta I. We can also otherwise write it as n1 xi eta will be equal to, this is -1 and -1, at which n1 has to be 1. So we can write 1 over 4, then 1 minus xi multiplied by 1 minus eta. So if you put xi equal to -1, so this becomes 2, this minus eta equal to also -1, so this term becomes 2, so 2 times 2, 4 divided by 4 becomes 1. At all other points this value will be 0. For example, at node 2 xi is 1, so you put 1 here, so this becomes 0, hence it will be 0, and similarly for other nodes as well. Similarly, we can write down n2 zeta eta will be equal to 4, and then this terms becomes 1 plus xi and 1 minus eta. n3 will be zeta eta equal to 1 over 4, then it will be 1 plus xi and 1 plus eta both, plus, and n4 xi eta will be equal to 1 over 4, and then 1 minus xi times 1 plus eta. So that when xi equal to -1 and eta equal to 1, if you put it here, so 1 minus minus 1, so this becomes 2, and this 1 plus 1, so 2 again, 2 times 2 4 divided by 4 becomes 1. At all other nodes this value will be 0. So let's summarize what we did so far. So we had one element of irregular size, so quadrilateral element, but we had something like this. Okay, so node 1 2 3 4 xy coordinates, we transformed that into a isoparametric element, so which has coordinates xi and eta. Okay, this is a square basically, and we have relation between the two coordinates. So x is given by is a summation of ni xi eta multiplied by xi, I equal to 1 to 4, and this corresponds to 4 nodes, so 2 3 and 4, and similarly y is also given by summation of ni xi eta multiplied by yi. So two coordinate system, and they are related by these equations, where ni we have already calculated, ni as a function of xi and eta. This type of transformation you probably did for finding out area of a quadrilateral having irregular shape, something like this one, where this is not a rectangle, it is not a square, even it's not a trapezoid. Then how to find out the area of the quadrilateral? One way is to actually divide into two triangles, and then you can also find out. However, here if we know how the one coordinate system is transformed into other one, and in the other coordinate system if it is very easy to find out the area. So in this case its length is 2, height is 2, 2 times 2 4 units. So we can, if we know how the area of the two coordinate system related, then we can just multiply that relation. Let's say if you know the ratio of area in this coordinate system to the area of this coordinate system, if you know that, then we multiply that ratio by the area in this transformed coordinate system to find out the area, the actual area. So let's do the same thing, because anyway we will need it later on, and this will also demonstrate how the coordinate transformation works and how it is helpful. So let us say we have to find out the area of this quadrilateral by using this isoparametric method. Yeah, so you must have done this in your mathematics course, but still I am going to repeat it so that you also have the insight. So in order to find out the area of this one, what you do, you divide it into many small quadrilaterals. So let us say your division will be something like from here, you are dividing here, so this is making half, this half of this and half of this, like this one. Similarly more half here like this one. So this this how you will do. So let's say this line 1 to 2 this corresponds to this line. And what do you see here? At this line, eta is constant. Okay, so here eta equal to -1. Here at this line, xi equal to 1. At this line 3 to 4, this is again eta equal to 1, and this line from 4 to 1 has xi equal to -1. So that means here xi is increasing or changing, but eta is not changing. So that really means here from 1 to 2 only xi is changing, eta is not changing. And if you go from 2 to 3, so 2 to 3, eta is equal to xi is equal to 1, so xi is not changing, remains constant as xi equal to 1, but the eta is changing. Or simply these lines corresponds to, if we just divide half, for example here, and this is half here, and then join like this one, then also this will just denote xi eta equal to 0. So this point, for example, half of this one, half of this one, and this point is half of middle way of line joining 2 to 3. Similarly, this also is the middle of this line 1 to 4. Then this point corresponds to the origin of this one. So it corresponds to 0, 0, for example, right? So if we divide this way, then we will have, let's say, the smallest we have one infinitesimal area which we can draw like this, like here, like this one, which will have, this one for example will have, this will be actually representing a constant xi. Okay, so d eta will be 0 in this case. So constant xi, so constant eta, so d eta will be 0, that is variation of eta will be 0, and this will have d xi equal to 0. Similarly, this will be d eta equal to 0, and this is d xi equal to 0. So let me repeat what I did here. So I made a cellular division here so that we get the small, very small, that is infinitesimal area here, so that we can take the infinitesimal, we can calculate the infinitesimal area. How we divided? We took half of it and half of it, and then drew the line again in the all the 4 the quadrants that we created. Again we made the similar division, taking half, 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 like this one, and so on. So basically this corresponds to doing, like, first we have the whole area, then we take half like this one, and then we took half of it like this one, and then further half like this and like this one, and so on. We keep on subdividing all sub squares created here, so that all the lines are either perfectly horizontal line or perfectly vertical line, and we are seeing the same area but in xy coordinate system here. So that means lines here and here all correspond to each other. If that is the way, if we subdivide, then obviously we will get the sub area in xi eta coordinate system. We will get a square like this one, where this line will be parallel to this line, meaning that eta will be constant or d eta equal to 0, and this line, vertical line, which is parallel to the eta axis. So that really means at this line d xi will be 0, means xi will be constant, that is there is no variation in xi, and as I said earlier, this will have d xi d eta equal to 0 and d eta equal to 0 here, and this is d xi equal to 0, and they correspond to each other, meaning that if you apply this transformation rule, then you can transfer from this shape to this shape and vice versa. Okay, once we know this one, next thing is to how to calculate the area. So in order to calculate the area, what we do, we just need to find out what is this vector. So let's say this is vector A, this is vector A, and this is vector B. So this is say is vector B. So d area will nothing but A cross B. We have to find out what is A, what is B. This is very, very small, so we can assume this is parallel to this and this is parallel to this one. It's a very, very small element. So in order to find out A vector and B vector, we have to first find out what is vector A. So what is vector A? Vector A equal to, this one will be nothing but, so this is in xy coordinate. So we have to see how the dx and dy varies in this line. So if we have dx, so we have dxi plus dyj when at where? At this line. So at this line means what? At this line means the coordinate is zeta, xi and zeta, and along this line d eta equal to 0. Okay, now we will come back to this one. So let's see if this is how they are related, and then how variation of one can be related to the variation of the two. What I mean is, we can say dx equal to, it is variation in x, so dx will be equal to del x over del xi, okay, times d xi plus del y over, sorry, del x over del eta d eta. Similarly, you have dy will be equal to del y over del xi d xi plus del y over del eta d eta. Or in other words, we can write it as dx dy equal to, then there is a matrix here. What matrix it is? This will be del x over del xi, then del x over del eta, then del y over del xi, and del y over del eta, this matrix, and multiplied by d xi and d eta. Now we have to see here, we have to find out A basically, and this A we can, so let's draw it again here. So our infinitesimal area, which looks like this one, and this one is A. This A vector, how do you find out? This will have, if this is dx, this is dy, then we can write A equal to dxi plus dyj, where dx is the variation in x when you go from here to here, and dy is the variation in y when you go from here to here. Okay, so but what is the variation? We can find out by using these equations. Okay, so let's write that equation again. So we have dx dy equal to this, you have del x over del xi, then del x over del eta, del y over del xi, and del y over del eta, and here you have d xi and d eta. Now at this one, as we said earlier, d eta equal to 0. Okay, only xi is changing. So that means if you put this equal to 0 here, so what do we get? We get both dx and dy, and what do we get? We get dx dy in this particular, for this line, for A we get dx and dy, which will be equal to simply dx over d xi and dy over d xi multiplied by d xi. That's what we will get. So hence A we can write it as A equal to dxi plus dyj is equal to, so dx is equal to dx over d xi I plus dy over d xi j, okay, multiplied by d xi. So this is what A is. Now coming back here, so for this one, this is B, our B, and for B again we can find out similar fashion. However, for this one is we have d xi equal to 0, because this corresponds to, in the xi eta plane, this corresponds to a vertical line. So vertical lines means xi is not changing. So xi equal to xi is constant. So dxi equal to 0. So coming back here, you can find out, we apply the same equation. So dx dy, and this equal to dx d xi, dx d eta, dy d xi, dy d eta. by the way, this we can call it a Jacobian matrix. So we can write this matrix is also we can write it at J, which is Jacobian matrix. So this is multiplied by d xi and d eta. Now here, as we have found out d xi equal to 0, so we'll put d xi equal to 0 for which case? On B basically, right? So that means we get simply in this case dx and dy for B will be equal to dx over d eta and dy over d eta multiplied by d eta. Okay. So beta can be written as dxi plus dyj, and which comes to be dx over d eta I plus dy over d eta j, and whole of it multiplied by d eta. Similarly, we already have A as dx over d xi I plus dy d xi j multiplied by d xi. So d area is nothing but equal to A cross B. So A cross B, so A is this one, B is this one, so we have del x over del xi I plus del y over del xi j cross del x over del eta I plus del y over del eta j, and then both of them also multiplied, so d xi and d eta also multiplied. Okay, so what do we get then? dA will be equal to, this becomes I cross I will be 0 and I cross j will be k. So we get this and this k, so we get del x over del xi multiplied by del y over del eta k, and then we have j, so j cross I equal to minus k, so we get minus del x del eta multiplied by del y and del xi k and multiplied by d xi d eta, or simply we can write it as dA is equal to, and this is a determinant, so we can write determinant of what? Determinant of dx, d xi and dy over d eta, so this is del x over del eta and del y over del xi. Okay, so determinant of this, and then you have k and d xi d eta. So this one, if you see earlier we had this one a matrix, we call it J. The same matrix we see the determinant of the same members basically. So we can say that this determinant is nothing but the determinant J. So we can say dA equal to determinant of J matrix or determinant of the Jacobian matrix, okay, and then del xi del eta, and K is the vector which is perpendicular to the element. Okay. So the total area of the element may be given by del dA, which is integrated over the whole domain. This or total area A is given by this equal to, now instead of using the xy coordinate, we can now calculate the area using the xi and eta coordinates. So we can write at J d xi and d eta. We can drop the vector, unit vector perpendicular to the area, because we know that area vector, direction of the area vector is perpendicular to the area. So we can drop it, this one here. So total area, which is scalar quantity, will be given by the determinant of the Jacobian multiplied by d xi multiplied by d eta, and the variation of d xi is -1 to 1. Similarly, the variation of the eta is from -1 to 1. So this is how we calculate the area of the element. Having irregular size, what kind of element? That's a quadrilateral element. However, the sides are not equal. General quadrilateral element which can be transformed into a square element, okay, and then we can integrate the Jacobian, the determinant of the Jacobian matrix over the whole domain of xi and eta, and then we can find out the area as given here. Now let's look at how we can derive the stiffness matrix. So the stiffness matrix, as we know that if big K has the members Kij, as we had in the last lecture video, so Kij is given by integration of over the whole domain, and what we have del ni del x multiplied by del nj del x plus del ni del y multiplied by del nj del y integrated over the whole domain, okay. And here we have, if the conductivity is constant, so we write K here. So we have to evaluate this one. In order to find out the stiffness matrix, we have to find out this. Now we don't have n defined in terms of x directly. What we have is ni here is a function of xi and eta. However, we know how x is related to xi and eta, and y, and how y is related to xi and eta. So we can utilize that to find out this one. So what we have is ni. So del ni over del xi will be equal to del ni over del x, then del x over del xi plus del n I del y, and then del y over del del y over del xi. And similarly here, del n I del eta is equal to del ni over del x, and then del x over del eta, plus del n I over del y, and then del y over del eta. So this relationship we can also write in matrix form, which will be del ni over del xi del ni over del eta. The whole thing will be equal to, here the matrix is nothing but the Jacobian matrix. So here del x over del xi, and so we have del y over del xi, and then we have del x over del eta del y over del eta, okay, and then multiplied by del ni del x del n I over del y, okay. So let us see whether it is correct. So what we have is del ni del x over del xi. So this is what the first term is. Second is del ni over del y, del ni over del y, del y over del xi. So this one is nothing but what we see is, earlier we call it a Jacobian matrix. So this is J transpose of that, because earlier we have seen this used to be here. Now instead of this is transpose of that. So this, instead of being this here, we have this here, and this is just a transpose of the Jacobian matrix. Okay. Now in order to find out the stiffness matrix, what we need is del ni over del x. So we have defined here del ni over del xi. So we need this one. So we will simply take this to this side. So we have del ni del x and del ni del y will be equal to, will be inverse of that. So J, so inverse of that, okay, and then we have multiplied by del ni del xi and del ni del eta. So this is what we have, okay. Now since we also need del nj over del x and del nj over del y, so similarly we just put it here del j only. Instead of I we can put j, and still that will be valid for nj. So del nj over del x, del nj over del y. So this will be again as, so Jacobian transpose, then inverse of that, and then we have del nj over del xi and del nj over del eta. Now remember that Kij is given by integration over the whole domain, the conductivity K, which is we are taking at constants, and then del ni del x del n nj del x plus del n del n, del ni, del ni, del y, and del n j del y integrated over the whole domain. Domain means here the area of the element. So here which is equal to k, and we have to find out this value. So how will we find out? What we have is these two systems of equations, del ni over del x, del ni over del y, and similarly for j. Now in order to find out del ni over del x multiplied by del nj over del y plus del ni over del y times del nj over del y, we simply need to dot product this. Okay, so dot product of these two vectors, that really means we multiply transpose of this to this one. So this is 2 by 1 now. So this is, or we can take transpose of this one multiplied by this one. So transpose of the first one, that really means this we have the transpose of whole of it. So this becomes this transpose, the transpose of the whole thing, like this one. Yeah. So what we mean is we will find out this. So just write here just this only. So we del ni over del x, del nj over del x plus del ni over del y, del nj over del y is equal to, we can write it as del ni del x del ni del y multiplied by del nj del x del nj del y, like this one. So this is what the dot product is. Okay, and this one, in order to get this one, we use the earlier equation. So this will be transpose of the whole thing that we wrote. So this was j transpose and inverse of what? Del n, del ni, del xi, and del n I del eta. So transpose of whole of it. So this is a transpose of this. Okay. Okay, and then this one. So this one we directly write. So this one we know this will be j transpose inverse of that, and then we have del n j del xi and del nj del eta. Okay, so this is the equation. so basically kij, also remember that d here, say d omega is nothing but d area basically, and d area, we from the earlier analysis we know this is simply equal to j multiplied by d eta and d xi and d eta. So kij simply becomes a small k, which is the conductivity like here, and then integrated over the whole from xi 1 to 1 eta minus 1 to 1 and eta also minus 1 to 1, and then this whole thing which is equal to this whole thing now. So this becomes J transpose inverse of that, and then we have del Ni over del xi, del Ni over del eta, this the whole thing transpose. Okay, then continue, then we multiply this by J transpose inverse of that, multiply again del N J over del xi, del N J over del eta, and so we are till here now, and then d omega is d area, which is equal to this one. So we write also here Jacobian determinant of the Jacobian matrix multiplies by d xi and d eta. So this is how you find out the stiffness matrix for this one. Stiffness, this is conductivity J, which is a Jacobian matrix, which is a function of xi and eta. This is also function of xi and eta, because Ni is a function of xi and eta. Similarly here Nj is also function of xi and eta. So whole thing will determine the stiffness matrix member ijth entry of this one, and we can find it for all the nodes. That means we can find out all the members of the global stiffness matrix K.